Now in this video, we're going to explore how U-SQL actually runs, how a U-SQL script executes in the Azure Data Lake Analytics system. And this is critical if you want to really become a developer of U-SQL, because far from just the language concepts, you have to know a little bit of how U-SQL is processing data. This will help you in debugging and optimization and performance tuning. So let's begin by taking a look at the job execution lifetime. You start on the left with a U-SQL script, which we often describe as a purely logical description of how to transform data from a set of inputs to a set of outputs. That is sent to, of course, a compiler, and the compiler may interrogate the U-SQL catalog, our metadata layer, to see how data is partitioned, to see how data is distributed, and these are all the tables and views, etc. That's our metadata system. So the compiler takes advantage of that, if possible, and generates a plan. So if you can consider the U-SQL script a logical plan, this would be the physical plan. This is what will actually happen sort of in our clusters to execute the job. The optimizer then takes this plan and then may remove nodes, may reorder nodes, etc., to just make this plan execute faster. Okay, and it takes advantage of a lot of information about how data is partitioned, where it is in the data center, etc., the nature of the code that's operating on it, etc. Now, you see the word plan on the screen here, and I just want to let you know, you may see this referred to or hear us talk about it and using several different words. Cluster plan is another way of saying this plan. It's also called the algebra. That's sort of its older legacy name. And of course, it is often simply referred to as the job graph, because that is the visual form it takes when you see it in the Azure portal or Visual Studio. So cluster plan, algebra, job graph roughly mean the same thing. Now the plan, which is now like the fully defined set of work, is sent to the job scheduler. And the job scheduler's primary goal here is to sort of put it in the system and now we're allocating AUs, that is compute resources, to execute the job. And the scheduler will then spin up a job manager, which will handle the work for the specific job. So the job manager's role is to begin the job, to see that all the pieces of work get done, and schedule that work on different nodes in our cluster. Now, in our cluster, what we have is a bunch of containers. Azure Data Lake Analytics implements those containers as VMs, so the work is isolated in VMs. And what the job manager does is schedule the work on those containers. And the pieces of work are called vertices. So a container we scheduled a container to run one vertex. And these vertices, these VMs, have their own local storage. Okay, we'll get to that in a second. But let's suppose they're reading data from Data Lake Store or from Blob Store. They'll read it from another network source. Okay, and so the vertices in their extract phase will read the data, and then all the processing that happens on the data will happen using the local storage on the Yarn containers. Okay, we will avoid reading and writing back and forth between Data Lake Store and these Yarn containers because it's much faster to use our local storage. Finally, when the job is done, the final outputs are then sent in parallel to Data Lake Store, and then the outputs are assembled. And when we assemble the outputs, that's actually called the finalization phase, which you can see in the Visual Studio and the portal UI when you look at the job graph execution. Okay, so this is an overall view of what's happening through a U-SQL job. And the key points to focus on: the U-SQL script is the logical plan. The physical plan is optimized. The work is divided into vertices that run on Yarn containers, implemented in this case as VMs, and that the extract and output phases, the things that really read the initial inputs and write the final outputs, they're the ones that read and write across the network into Data Lake Store, and internally we use our own internal storage on the Yarn containers for intermediate data. Okay. Next, now I talked about this logical plan here. Let's break it apart. When a U-SQL script is transformed to the physical plan, you see, I mentioned there are pieces of work called vertices, and the vertices are grouped together, okay? And when they're grouped together, they're called stages. Okay, so each stage you'll have at least one vertex. Okay, and the vertex, the number of vertices in a stage indicates how parallelizable that stage is. So in this middle picture, you can see there's one input, one output. There are three stages that linearly just depend on each other. The first is parallelizable by 8, the second by 10, the second by 4, and then the last one by 2. Okay, so there's a number of total stages, but the parallelization is also per stage. And of course, how we visualize this is this job graph. Okay. Now, what happens is these vertexes are pieces of work. And remember, to execute one, we'll allocate an AU or assign an AU. That's one yarn container, which is implemented as a VM, so it's isolated. And the VM has 2 cores and 6 gigabytes of memory. And in the future, we're going to think about ways of saying, hey, this assign this stage or this operation more AUs per vertex, right? Because some work requires just more memory or more cores, depending on what you're trying to do. Okay. So I want to also clarify the difference between AU and vertex. So a vertex, again, is a piece of work. And what influences that is the amount of data, what the script is actually doing, etc. An AU is a container, right? It's an amount of compute resources in terms of cores and memory. So whereas with the vertices, you influence that by the amount of data you have and the specific operation in your script, the number of AUs are directly controlled by the developer. So you can say, I wish to assign 50 AUs of work, right? You cannot say, I wish to assign 50 vertices. The vertices are they're inferred from the size of your data typically and the kinds of operations you're doing. You can influence it by changing the operations and providing sort of U-SQL hints, which is a more advanced topic. Okay, so now we know that a job is compiled into a cluster plan, and then that's visualized as a job graph. And we know that this compilation process produces vertices, okay, inside each stage. And what's happening in each stage is, let's take a look at what's actually being sent to each vertex, okay? So when you compile a script, you have these resources, we call them, right? Now, some of them are just the normal U-SQL resources, right? Like our own runtime bits. Others are resources you provided, like let's say a reference data file, or .NET assemblies that you've asked to be deployed, or text files you've asked to be deployed on each vertex. So that's sort of like the entire set of job resources. And what happens when a U-SQL script is compiled, surprisingly, because we're so .NET focused with U-SQL, you may think that it's automatically compiled to manage code via C#, and that actually used to be true. But that's not necessarily true anymore. In fact, even though we use C# as a language, if you're not doing anything that requires unmanaged code, we will actually just generate C++ code and create an unmanaged code for your Vertex execution. It's only if you're doing something that requires writing custom code in C# or calling a .NET function that we haven't inlined in some way, where a managed DLL will be created and used. Okay, and why do we do the C++ part? Because it's like 20% faster if you can just stay in unmanaged code. Now, again, all this happens behind the scenes. You don't need to worry about it as a developer. It's just one of the ways I wanted to illustrate that this system is trying to become more efficient under the covers. Okay. The other resources include the algebra and, of course, the files that the user has asked to be deployed, additional DLLs, reference data, etc. And those are deployed then to containers. That is the yarn containers, the VMs I said, and they'll be run. Okay. And now you're probably wondering, why in this on the far right, why do some stages contain so many vertices and some contain less? And why, what explains this organization? So again, I mentioned before that all the vertices in a particular stage tell you how parallelizable that individual stage is. And another way of thinking about this is it's based on the amount of data that's available, how parallelized it can be, in relation, of course, to the operation that's being done in the stage. So the top stage here seems relatively parallelizable, and what's happening is that each vertex represents the same code, meaning the same operation, being done on different pieces of the same input data. Okay, so if you have let's say 100 terabyte comma separated value file, you may have hundreds of vertices. Each one is doing the same thing, but on a chunk of that file. Now, as you get to other kinds of stages, let's look at the bottom one. Things may not be as parallelizable, right? And it may be because there's just much less data. This sort of graph where you see the shrinking of vertices is very indicative, for example, of a lot of aggregation. Or it could be that the operation you're doing at the very end there is something that requires sort of all the data to be sent to a small number of nodes. So sorting is an example of something that would tend to create smaller number of vertices in a stage. So that's what controls the number of vertices in a stage. And again, you can't control the number of vertices, but you can influence it through the number of data and the operations. And there are hints we have in U-SQL that help you sort of push the number into in a direction that you might need. Okay, so now let's just take a look at what happens when you run with parallelism, different parallelism values. Parallelism here means the number of AUs. So if you just ask for 1, then what happens is linearly only one container will be active as it executes through the job graph. If you ask for 4, up to 4 will be active as you execute the job graph. There's no guarantee that 4 will always be running. At least 1 will. But remember, when you say parallelism of 4, you're reserving compute capacity. You're not saying, you cannot force a job to be parallel, okay? And take a look at the last picture, the very bottom. Again, there's a stage where there are only 2 vertices. So even though you've asked for 4 containers, only 2 can be used in that stage. Okay, that's very important to remember, again, that the parallelism that is possible in a job is also dependent on which stage you're in. Now, when you open Visual Studio or the portal, you're going to see the stages shown in a format like this. Let's just go over what's being said. The first is the number of vertices, in this case 5. The number below that is the number of seconds per vertex, okay? And then specifically, this is the average time. And so this is a good average time. We like vertices that execute in a few seconds. It's not uncommon to have a vertex that executes in a minute. As you start getting much longer vertices, you start wondering like if the right thing is happening. There is a 5-hour limit to the length of an individual vertex. So you do have to keep that in mind. And you'll get warnings if you start coming close to that limit. And the number of rows, of course, this is a very small stage. It only in total produced or consumed 5 rows, produced 5 rows. And then you can see the amount of data that's been read or written. And this stage is green because it's 100% complete. So it was a successful stage. Now you may notice that some stages have a little bit of orange. And you can see this usually toward the end of the stage. What that means is that a vertex actually failed, but we retried it, okay? Now, vertexes can fail for a number of reasons. They could fail for like very systemic reasons, meaning it's our service is having a problem, hey, but let's say a router went down or a machine had to be rebooted. No problems. What we'll do is we'll reschedule the vertex on a different container. So there's an automatic kind of retry in the system. And the evidence that we're very resilient to the failures is the fact that you see the retries indicated in this yellow color on a stage. So this stage was successful. It's just that one of the vertices had a hiccup. Okay. Now, if you see a bunch of this happening over and over, maybe there's something funny going on with the vertex. But usually these will be system errors that we can route around in our cluster. Now, by the way, not all vertex failures mean the stage will be successful. Clearly, there's some errors that mean this job should not proceed. So for example, if your user code in a vertex throws a null reference exception or a divide by 0 exception, there's no point continuing the job because we'll never, if you retry the vertex, it will still fail. So those cases will yield to quickly failing the job. Okay. Now, another thing that you should notice when you're using U-SQL, and this is just to help you understand what's happening in the system, is that if you're using UDOs at the bottom of the stage, you'll actually notice they've been annotated with the platform type. So you might see .NET or Python, and in the future even, we're planning on introducing Java UDO, so you'll see JVM there. Now, if you double click or right click and say show vertex operator view, the operator graph is shown. And so what this lets you see is what exactly happened inside an operator. So you can see, again, if you look in here on the right, you can see exactly where that .NET code is. And specifically, you can see the name of the class that's used. So this really helps you identify where problems are and get to the root of these issues. And typically what we find is when people use a lot of complex UDOs, if you see a stage that's slow and the average vertex time is very long, like 30 minutes, it tends to be because someone has written a very inefficient UDO. So how do you find the UDO? You look in the operator graph and you can zero in on it. Okay, and there's an example of the actual name for this stage, or this class, the UDO class. Now vertices, just like stages, have a relationship. Every vertex essentially has a parent vertex, okay? And they're dependent on the output of another vertex. Except, of course, the very initial vertexes that are doing the extract, which are just reading from a file. So the key points I want to sort of talk about here are, first, the vertexes don't have to start, and stages don't have to start in order. You can see in the picture in the middle on the top, vertexes in the second stage can actually begin even while vertexes in its parent stage are still running. And that's because the data for those two running vertexes in the blue, their data is already prepared, so they can start running. There's no point in waiting. So that's one thing that you'll probably see in the job graphs, is that child stages can begin even if the parent stage hasn't finished. The second concept I want to introduce to you is the concept of when you think about the fact that vertices have this lineage, right? They have a parent of the source of the data. And so this is a dependency chain. And you can always think of in a graph, the longest running vertex, or the longest chain of dependencies is called the critical path, right? And this sometimes it's actually very useful in debugging. Our tools will help find the critical path. So if you were debugging a job and you want to see, what was the chain that took the longest to execute, you'd go find and filter for the critical path. Okay, it doesn't mean the critical path is wrong or somehow critical in a bad sense. It just means that's, to use a metaphor, the longest pole in the tent. And finally, we have a concept called vertex determinism. So let's go ahead and say, the first two vertices have executed and the final one has failed, right? Now, by the time the final one has failed, let's say the middle one is gone, right? Like, now we have a problem, right? We have to rerun the vertex, but we don't have the data descended. Well, vertexes are deterministic, meaning we can actually just regenerate the input for any given vertex all the way back, if needed, from the original source data. Of course, that's expensive a little bit, right? Because you have to regenerate some work. But this is one of the reasons we can actually rerun a vertex very reliably, because we know the full plan to do the work. And if there's a problem and we need to regenerate data, we can go all the way back to the source data and regenerate it. Okay, and I mentioned before about vertex allocation, meaning how many vertexes are in the job or by stage. Again, it's not directly controllable. The three things that are going to influence it are how big your data is, like the size, as well as how it's partitioned. That's why you should really pay attention to U-SQL tables and how you distribute and partition the data. It has a dramatic impact on performance, especially as your data size grows. Number two, what are the exact operations you're doing? So there are some very expensive operations. Ordering by will tend to force a lot of data to a small number of vertices. So be aware of that. Or certain more complex operations like using a reducer UDO on a column, they can lead to that same effect of pushing a lot of data to a small number of vertices. Okay, and especially when you write reducers, you have to be very careful. It is very easy to accidentally write a reducer that forces all data to just a single vertex. Okay, and what you need to do is learn how reducers work and how to parallelize the reducers so that you take advantage of being able to scale out as much as possible. And that word for this parallelizable reducer is called a recursive reducer UDO. Okay, and finally we have data hints. So there are things you can tell the script, not about, hey, do this, but describe your data. These are called data hints that will help the optimizer figure out what to do. So a simple example is row count. So sometimes, you can actually tell the system on a given expression, hey, this U-SQL statement is not going to generate 1 trillion rows. It's going to be a small set of rows. So if you're doing a join, for example, and it knows that the right side is known to be small, then it will do the join a little differently. And it could have a dramatic impact on performance, right? Because a small join where the right side is big, where the left side is small, you'll do it very differently. Another example is a skew factor. If you're doing a join, if there's a join key, you can say that, hey, the distribution is kind of split evenly between the two sides, right? Or it's biased in favor of one way or the other. Don't want to go over all the hints here, but these are the kind of things you can do. And again, these are hints. The optimizer is free to disregard them because they may receive contradictory hints, or it may just realize your hint is not needed or incorrect in this case. So they're not guarantees that they'll be obeyed, but they definitely will influence the vertex allocation and thus performance. And that's it. That's the conclusion of how U-SQL executes in the Azure Data Lake Analytics system. As always, please feel free to contact us in the Azure Data Lake team. We'd be happy to share more on this topic. Have a great day.